So we saw here when we had a ratio of lengths of 1 to 3, the ratio of areas was 1 to 9. When we had a ratio of lengths of 1 to 2, the ratio of areas was 1 to 4. The relationship here is just like the units. This would be in inches, this would be in square inches. If we take that 1/3 or 1 to 3 and we square that ratio, what's 1 squared? 1 and 3 squared? 9. We do the same thing down here. We take this 1 to 2 ratio and we square it. What's 1 squared? 1 and 2 squared? 4. We get the ratio of areas. So the ratio of lengths squared is the ratio of areas. So if I know the ratio of lengths, or the ratio of sides between two similar figures, I can find the areas of one if I know the area of the other. Now this is most useful if we have kind of an irregular figure like this. I know that's kind of mean of me to draw something like that. So let's see, what we know here is that the radius of this arc of a circle here is 6 inches here, and over here it's 8 inches. So this figure has been enlarged. And we know the area of this one here is going to be 676 square inches. What's the area of this one going to be? Well, we start out looking at the ratio of lengths. The ratio of lengths is 6 inches becomes 8 inches. Now I'm going to reduce that just to make my life easier. Both of those, first of all, the inches cancel out and both of those divide by 2. Gives me a 3 to 4 ratio of lengths. So now to find my ratio of areas, I'm going to take 3/4 and I'm going to do what to it? Square it. 3 squared is 9. And 4 squared? 16. So the ratio of areas is 9 to 16. The 676 comes from the smaller one. That goes on top. So I'm looking for the area down here. I'm going to cross multiply and divide. So 16 times 676 divided by 9. 1201.78. I'll keep it a little bit simpler on a test. A little bit. Let's say I have a box, and the sides on this box here, 2 inches, 3 inches, and 5 inches. And this one is 6 inches, 9 inches, and 15 inches. Those boxes are similar. You can see every side is multiplied by 3. So the ratio of lengths again Well, 2 inches became what? 6 inches. I reduce that. Inches cancel out. 2 over 6 becomes 1 over 3. And again, I could have used any pair of sides I wanted to. I could have done 3 becomes 9. Again, that would reduce to 1 over 3. Or I could have done the 5 becomes 15. Again, that would reduce to 1 to 3. So my ratio of lengths here is 1 to 3, no matter what. Let's find the volume of this one. Well, that's 2 inches times 3 inches times 5 inches, otherwise known as 30 cubic inches. This volume over here, though, is 6 inches times 9 inches times 15 inches. Otherwise known as 810 cubic inches. My ratio of volumes is 30 cubic inches over 810 cubic inches. Well, first of all, the cubic inches cancels out. Both can divide by 10. Gives me 3 over 81. Both of those can still divide by 3. Gives me a 1 to 27. Is there a relationship between my ratio of sides and my ratio of lengths and my ratio of volumes? We probably predicted it from what we did with areas. If I take my ratio of lengths, instead of squaring it, I need to cube it to the power of 3. 1 to the third power is just 1. 3 to the third power, 3 times 3 times 3 is 27. So the ratio of volumes is just the ratio of lengths to the third power, or cubed. So I could have a really weird shape like that. Let's get back here. And let's say this one goes from being 10 feet tall to this one being 15 feet tall. The volume of this first one, let's say that it is 940 cubic feet. Let's find the volume of this one. Well, my ratio of lengths is 10 feet to 15 feet. Of course, the feet cancel out. I'm going to reduce that by dividing both of them by 5 to give me a 2 to 3 ratio of lengths. My ratio of volumes is found by doing what to that ratio of lengths? Cubed. What is 2 cubed? Careful. 2 times 2 times 2. 8. There we go. 3 cubed? 27. So our ratio of volumes is 8 to 27. The 940 comes from the figure of the 10. That's on top. So 940 goes on top here. So we're looking for this volume down here. So 27 times 940 divided by 8. $3,172.5. 3,172.5. Those are in feet, so this will be in cubic feet. Is my volume. What do you think? A little bit easier than the areas and volumes? If you think back when we did measurement, if I wanted to convert 3 square feet into square inches, we had to do the same thing there. You know, the ratio here, the ratio of lengths is kind of like a conversion factor. Only here, when we were converting, since this was square feet going into square inches, we didn't use 12 inches in 1 foot. We used 144 square inches in 1 square foot. It was the 1 to 12 squared, which is 1 to 144. Cancels out, you get your, what, 532 square inches or whatever. Or if we had cubic, you know, let's say we had 324, let's go with. Cubic feet, and I want to know how many cubic yards that is. Same thing. We started out with the 324 cubic feet, but our conversion factor was changed. 1 yard is 3 feet, but since it's cubic yards, we had to cube it. 3 times 3 times 3 is 27. Gives us 12 cubic yards. So it's the same concept. When you're dealing with square units or cubic units, you have to adjust your conversion factors. Okay, our last thing we want to look at for today is starting on ordered pairs. There's a lot of times where we have pairs of numbers that we have to put together. Pairs of related numbers. You know, it could be height and weight. It could be, you know, years of service and days of personal time or whatever. Let's say somebody who has been on the job for 7 years gets 3 days of personal time. I'm actually going to write it out like this. 7 years, they have 3 days of personal time. Well, rather than writing out the words like that, we can write it like this. 7, 3, put it in parentheses. That's what we call an ordered pair. Kind of like with our place values and our whole numbers, we know which number is which and what each number means by its position in that ordered pair. We know that the first number means years and the second number means days of personal time. Now, if you go way back to our first couple weeks of class, when we were talking about dealing with negative numbers and integers, we represented numbers graphically. With a number line. There's a couple of different ways we could represent numbers. We talked about vectors, like the vector for 7 starts at 0 and goes to 7, which was the way we needed them for adding, subtracting, and stuff like that. But if we're just representing the number, the other way we could do it was just put a dot at 7. That dot represents the value of 7. We used the vector as kind of a mechanical representation so we could add and subtract and do stuff with them. But here, this is an ordered pair. I want to represent the numbers 7 and 3 together. On a single number line, that's tough to do. I mean, I can put the 7 there, and I can put the 3 here, but showing they're related is kind of tough. I suppose I could connect them, but then the order matters. So I'd have to use an arrow or something to show that this one, the 7 comes first and the 3 comes last. Well, that would get pretty crowded and tedious. So a man by the name of René Descartes, a couple thousand years ago, came up with something called the Cartesian coordinate system. And what Descartes said is, if I'm going to represent a number like 7, 3, that pair of numbers that has that relationship, I'm going to take a number line, just like I always have, with 0 in the middle, positives to the right, negatives to the left, just like we always have. But then I'm going to take a second number line, and I'm going to go through the 0 of that first number line. The second number line is going to go up and down, with positives going up and negatives going down. And its 0 is at the same 0 as the other one. So that spot there is what we call the origin. It's the origin because everything starts there. Everything originates from there. Both number lines have zeros at that point. Well, this first number line, the horizontal one, is often referred to as the x-axis. It's usually what we more often called the independent axis. The vertical number line is called the y-axis, or often called the dependent axis. Well, where do the terms independent and dependent come from? Well, think about what we're doing here. This is the years they've worked there. 3 is the number of days of personal time they get. Well, 7 is independent. You can pick anybody and their number of years of service, is independent. It's what you pick. But once you know how many years of service they have, their number of days of personal time is determined by that. It depends on the first number. So the value of this variable depends on the value of this variable. Not always an exact correlation like this one, but there's usually a relationship. So to represent 7 years of service, which would be this value right here, and 3 days of personal time, which would be this value right here, to show that they go together, we trace them out until they intersect. That dot right there represents 7 down here on the x-axis, and 3 over here on the y-axis. So that coordinate is 7, 3. So let's say I put a dot right here. What's its coordinate? -5 goes first. The horizontal axis goes first. That's the -5. And 4, the vertical axis, goes second. So how about this dot right here? -2, -6 is where it's at. And here, that one's at 4, -3. So we have the origin here. We have the axes. We also have something called quadrants. Quadrant just means 4 sections. This is the first quadrant because both numbers are positive there. In most real-life applications, that's the only section of the graph we use because both numbers are positive. From there, we go along with trig, which goes around counterclockwise. So we just go second quadrant, third quadrant, and fourth quadrant. Those are just Roman numerals, 1, 2, 3, 4. If I had a point right here, what's the coordinate of that point going to be? Well, the x-coordinate is 2. The y-coordinate is 0. Any point that's on this x-axis, the y-coordinate has to be 0 because it goes through 0 on the y-axis. If I have a point right here, what's its coordinate? This time x is 0 and y has to be 4. Any point that's on that y-axis, the x-coordinate will be 0 because it goes through the 0 of the x-axis. This is an incredibly important tool for expressing solutions to certain equations. Let me show you an example here. If I take an equation like 7 equals 3x minus 2. We solved equations like this back in about the third week of the semester. What did we do? We add the 2. So 9 equals 3x, and then what? Divide by 3. So 3 equals x. But what if I have 13 equals 3x minus 2? It's a different equation, but if I go to solve it, my steps are going to be exactly the same. I'm going to add 2. That's gone. 15 equals 3x. And I'm going to divide by 3. I get a different answer, however. 5 equals x. I might have 22 equals 3x minus 2. Again, the steps are exactly the same to solve. I add 2. Divide by 3. Different values of x, but in every equation, at exactly the same steps to solve it. This is what is referred to as a family of equations because they all have the same form here, just a different value on the other side. I can represent that whole family of equations like this. Y equals 3x minus 2. And now what I have here is all the possibilities. Every different possible number I can put in here is represented by this general equation here. The problem is there's an infinite number of numbers I can put in there for y. There's an infinite number of these equations in this family. So to represent their solutions, I can't just list them out because there's too many of them. So we usually represent them graphically on this graph. To do that, what I do is make a table. So y equals 3x minus 2. Now, rather than picking values for y and figuring out what x has to be, like I did in these last couple of examples, it's usually simpler to pick values of x and figure out what y has to be. Now, what I'm doing is I'm going to pick values of x that are spread out across the x-axis here. So I might do like a -3, -1, 0, values that are spread out. So let's do x is -3, -1, 0, 2, 4. Let's see what happens with that. So if x is -3, y has to be 3 times -3 minus 2. Yeah, 3 times negative 3 is negative 9, minus 2 is negative 11. So that gives us the ordered pair of negative 3, negative 11. I can probably squeeze that on here. Negative 3, negative 11 would be like right down here. Somewhere down here. If x is negative 1, y is 3 times negative 1 minus 2, which is 3 times negative 1 is negative 3, minus 2 is negative 5. So that gives me the ordered pair negative 1, negative 5. Right there. Does everybody see where I got the negative 5 from? Any questions on it? I just put this value in where x is here and I solved it. So if x is 0, y equals 3x minus 2, so it's 3 times 0 minus 2. Ends up being negative 2. Good. So 0, negative 2 is right there. If x is 2, y is 3 times x, or 3 times 2 minus 2. 3 times 2 is 6, minus 2 is 4. So we got 2, 4. 2, 4 is right there. And if x is 8, y is 3, x is 4, y is 3 times 4 minus 2, excuse me. 3 times 4 is 12, minus 2 is 10. So it's 4. 10, somewhere up here. Well, if my graph was scaled correctly, this forms a straight line down through my graph. That line represents all of the solutions to this equation. If I pick a point, let's say I pick a point right here. I trace it down here to x is 1. Trace it over here, y is 1. So 1, 1 is a point on that graph. X is 1 and y is 1 would make that equation true. Or I might have a point somewhere in here. X is negative 2. Y is negative 8. Negative 2, negative 8. That's a point on that line. It's a solution to that equation. Every point, I could pick a point here where x is negative 1.4 and trace it over to find my value of y. That's all the solutions to that equation. Now, not all equations are going to form lines. We might have equations like this. Y equals x squared. Let's see, what am I going to put in here? Plus x minus 6. So when I go to graph this, I pick values for x. I'm going to figure out what y is. I might try negative 3 for x. So y is negative 3 squared plus negative 3 minus 6. Negative 3 squared is 9. 9 plus negative 3 is 6. Minus 6 is 0. So it gives me a point negative 3, 0. That's a point right there. Let's try x equals 0. So 0 squared plus 0 minus 6. Well, those are all zeros except for the minus 6. That's going to be 0, negative 6. So that's a point right there. Let's try positive 3. So it's 3 squared plus 3 minus 6. 3 squared is 9. Plus 3 is 12. Minus 6 is 6. So that's a point at positive 3. Positive 6 right here. Well, obviously not going to be a line, right? when we're dealing with points like this that are not lines, or graphs like this that are not lines, a lot of times we get a few points on the graph like this, and then we go back and have to decide where do we want to pick our other points. I need to know what's going on in here somewhere. So I'm going to have to pick either x equals 1 or x equals 2. Kind of want to know what's going on in here, so x equals -1 or -2. So I pick those points and use them to figure out what the rest of that graph looks like. So I'm going to pick x equals 1. So that's going to be 1 squared plus 1 minus 6. So that's 1 plus 1 is 2 minus 6 is a -4. So I got 1, -4. So 1, -4 is right there. Let's try -1, see if that helps us much. If x is -1, y is -1 squared plus -1 minus 6. -1 squared is 1, plus -1 is 0, minus 6 is -6. So -1, -6 is right there, right next to the other one. Looks like that. To give me a little bit better idea, I'd feel better. Let's pick +2 here and put that in. X is +2. Y is 2 squared plus 2 minus 6. Comes up to be 0. So 2, 0, and I plot that point right there, 2, 0. If I kept going, I could find -2 would be -2, 4 somewhere in here. Now I've got a pretty good idea that this graph looks something like this. I can sketch it in. So when you're graphing, you can't just pick a certain number of points and hope that tells you the graph. You've got to pick a few points, get them on there, then you have to look and see where else do I need points so I can figure out what this looks like. For Wednesday, there is a new homework. It'll be due Wednesday. There's a quiz due tomorrow yet. I'll get to that in a second. But along with that, there's going to be a worksheet that I'm going to post in Blackboard. What this worksheet looks like is this. It's a bunch of tables and equations. And it's asking you to graph each equation. So you fill in the table, plot the points, figure out what the graph looks like. Some of them will be lines, some of them will not. And there are 10 of them on here that I'd like you to try to graph. If you can't figure out the graph, at least figure out some of the points and get a couple of points on the graph. And we'll go from there on Wednesday. This is what we'll start our discussion with on Wednesday, is this worksheet. And yes, as always, oops, where'd it go? Get back here. Oh, I lost my Word document. That's okay. There is a new quiz that is due tomorrow at 11:59 p.m. My Word document shut down when I closed down my graph, so I can't write it down for you. But yes, new quiz tomorrow at 11:59 p.m. Homework and worksheet for Wednesday. You guys have a good day.